Welcome to CSA I Think Tinker Learn. This is part of my System Design Essential series. The goal here is to give you a solid mental model of system design topics. We're breaking down of the evolution of HTTP today, moving from blocking queues to past the independent transport of the future. This is a concept first introduction to help you build a system design foundation quickly. If you want to see a deep dive on the trade-offs or a specific case study, let me know in the comments. No fluff, we'll get into the technicals in this one. Before we begin, please hit that like button, share this video, and subscribe. And check out our companion site. The link will be in the description. These are the GitHub pages, and here you can find all the articles. This is a work in progress. As I move ahead, you'll find more articles getting here. Today we are putting a deep dive on this article. Okay, let's get started now. To understand HTTP, think about the physical traffic. Um, every design decision that you map to a physical intuition. HTTP 1.1 is a sequential queue. If the toll booth is slow, the whole highway stops. HTTP 2 is like a shared foundation. We added lanes. But if the bridge itself collapses, all lanes fail. HTTP 3 is the independent tracks model. Individual pods moving in their own rails. If one pod breaks, the other one just zoom past it. Let's look at how we got here. In the early days of HTTP 1.1, the atomic unit was the connection. On a 50 millisecond round trip network, opening a new TCP connection costs you 100 milliseconds of overhead for the handshake before a single byte of content moves. Doing this for 90 plus resources on a modern web page is catastrophic. The first major fix was keep alive, opening the pipe once and amortizing that handshake cost by spending multiple sequential requests through the same open door. But even with keep alive, we hit the breaking point. Application head of line blocking. HTTP 1.1 used strict FIFO ordering, first in first out. You could send multiple requests at once via pipelining, but the server had to respond in exact order that they were received. If the first request was a slow database query for the video, and the next 50 were tiny CSS files, those CSS files would sit in the server's buffer waiting for the video to finish. One slow query poisoned the entire pipeline. This led to what I call as the duct tape era of the web. To bypass head of line or HOL blocking, browsers started opening 6 parallel TCP connections per domain. Engineers used domain sharding, spreading images across image1.cdn.com, image2.cdn.com, just to trick the browser into opening more pipes. We used CSS spriting and JS bundling to combine files. These weren't best practices. They were anti-patterns born of protocol limitation. We were optimizing for the network, not for the cache. HTTP 2 changed everything with the binary framing revolution. We moved from passing text to routing structured binary, speedy, and later HTTP 2 introduced a new framing layer where every communication unit is wrapped in a binary frame with a 9-byte header. The stream ID is the linchpin here. It tags every chunk of data, allowing the receiver to reassemble scrambled frames. For the first time, true concurrency was unlocked. This enabled HTTP2 multiplexing, which finally fixed application layer HOL. Now, multiple virtual streams execute simultaneously over a single TCP connection. Frames from different files are interleaved in any order based on priority. You get one handshake and zero application blocking. Interestingly, all those HTTP 1.1 workarounds like bundling now actually hurt performance because they break cache granularity and priority management. Under the hood, HTTP2 also solved the problems of stateless redundancy via HPACK. Standard HTTP headers are incredibly repetitive, sending the same user agent string over and over and over again. HPACK uses a static table of 61 pre-agreed common headers and a dynamic table built over the connection's life. We stopped sending hundreds of bytes of redundant strings and started passing 1 byte stateful pointers. This is a massive bandwidth saver for a micro request. But there was a hidden trap. HTTP2 streams are an illusion. TCP only sees a single byte array. TCP guarantees a strictly ordered, reliable stream. If one packet is lost in transit on spotty Wi-Fi, the OS kernel holds back all subsequent packs, even if they belong to a different, unrelated streams, until the lost one is retransmitted. This is TCP head of line blocking now. On a connection with 2% packet loss, HTTP2 can actually be slower than HTTP 1.1. To fix this, engineers realized they couldn't patch TCP. It's ossified inside OS kernels and middle boxes. So for HTTP3, they abandoned TCP entirely. They built QUIC on top of UDP. UDP isn't used because it's unreliable. It is used as an empty canvas. QUIC rebuilds reliability, congestion control, and flow control from scratch in user space rather than the kernel, allowing it to evolve much faster than traditional TCP. The architecture masterstroke of QUIC is per stream loss recovery. Because streams are natively understood by the transport layer, not just the application, they are decoupled. A lost packet now only pauses its specific stream. If an image packet is lost, your JavaScript and CSS streams keep flowing perfectly. Total isolation. Transport level HOL blocking is finally eradicated. QUIC also speeds up connection establishment by making mandatory TLS 1.3 direction from the transport handshake. This drops the setup from 3 round trips to 1, even 0 RTT for returning clients. However, 0 RTT introduces the replay attack zone, where attackers can capture and resend packets. To mitigate this, we restrict 0 RTT to idempotent methods like get and return a 425 too early status for any state changing request. One of the coolest features of QUIC is connection migration. Under TCP, your connection is identified by your IP and port. If you walk out of your house and switch from Wi-Fi to 4G, your IP changes and the TCP connection dies. QUIC uses a randomly generated connection ID that is decoupled from your network address. Your phone can change networks, and the download continues seamlessly because the ID stays the same. When we synthesize these features, notice the evolution of compression. HTTP2 use HPACK, which assumes strict in-order delivery. Because QUIC streams can arrive out of order, HTTP3 requires QPACK. QPACK separates the encoding and decoding states to prevent state corruption when packets are interleaved. We also use alt SVC headers to let a client know that an HTTP 1.1 or HTTP2 server is capable of upgrading to HTTP3. As a senior engineer, your heuristic should be about context. In a controlled data center environment with near zero packet loss, HTTP2 is often better because the CPU overhead of QUIC's user space processing isn't worth it. But for mobile APIs and CDN Edge, where the public internet is hostile and connections are spotty, HTTP3 is king. Now, a question for you. Have you started seeing the benefit of HTTP3 in your own production matrix? Or has the complexity of UDP routing caused more headache than it has solved? Let us know in the comments. Please like, share, and subscribe, and I'll see you in the next one.